Hey everyone, so thank you so much for having me. If you have questions at any point, or if a plot that I put up isn't clear, just put your hand up and get me to explain. Don't let me ramble on without having explained what I'm talking about. So just to give you an outline about what I am going to be talking about, I'll start with a really broad motivation about why what I work on is interesting. Then I'm going to talk specifically about gravitational instability, how that relates to the motivation. And I'm also going to start tying this in with observations of real systems as well and interpreting those observations. I'm going to spend a fair bit of time actually talking about works in progress that I have at the moment, because it's stuff that I'm excited about and stuff that I think you'll find interesting. And hopefully you can help me solve some problems that I'm having as well for work that's not finished. And then I'm going to summarize. So to start at the beginning then, this image is of the Chajnantor Plateau in the Atacama Desert in northern Chile. It's the site of ALMA, the Atacama Large Millimeter Submillimeter Array. This instrument that you can see here, it's actually an antenna, it's an array of antennas, has opened up to us a whole new level of planet formation. We've been able to see things that we were never able to see before in very high resolution millimeter wavelengths. That millimeter wavelength meant that we were able to probe down into the midplane of the disk and see a significant amount of the disk and see planets as they are actually forming. So we know that statistically speaking from exoplanet search missions like Kepler and like TESS, that every star statistically has at least one planet around it. There are at least 400 billion stars in our galaxy. There are about 400 billion galaxies in the universe. If you put these things together, it tells us that there are at least 10 to the 23 exoplanets in the universe. It's an awful lot of exoplanets to study. So studying these exoplanets can help us to answer what I think are some of the most fundamental questions that astronomers have, such as how did Earth form? Earth is special. Nothing else in our solar system is really like it. We have an abundance of liquid water, but we also have a bunch of other properties that we think may have been important for the evolution of life, such as a very thin lithosphere, which gives us geographical relief, which may have been, important in things like evolutionary drivers to geological pressures, for example. So understanding how Earth formed and why it's different is really important. But also, how did life begin on Earth? If we can search for signs of prebiotic chemistry, such as precursors to amino acids, so things like formamide, for example, are some of the building blocks to amino acids, which we ultimately need to form DNA and to form proteins that we need for life. If we can study these molecules, perhaps it will give us a clue as to how we made this jump from inert molecules to replicating, walking, talking human beings. And the biggest question, I think, philosophically, theologically, and for society is, are we alone in the universe? This question, I think, is almost impossible to answer until we have conclusive evidence of life elsewhere. But what we can do is we can quantify the frequency with which Earth-like planets form. And indeed, that's the first step on the ladder towards maybe answering this question. So we have here what I like to call the exoplanet architecture. So you can see here, so this is Earth radii, so this is planet size increasing this way. This is period, this is how far away that is from the host star in days. You can see there are basically these subcategories of planets. So you have hot Jupiters, planets that are many times the mass of Jupiter, that are orbiting sometimes inside the orbit of Mercury around our host star. We don't have anything that's analogous to this in our solar system. We also have cold gas giants, which again can be many times the mass of Jupiter, orbiting very far away from their host star. In the middle here, we have ocean worlds and ice giants. We also have rocky planets like the terrestrial planets that we find in our solar system. We also have what we call lava worlds as well, which are rocky bodies that orbit incredibly close to their host star, and are usually tidally locked. And the key question is, how do we explain this diversity? What I've shown you just has this huge amount of variety in the exoplanet architecture. Why are they so different? What's happening? So exoplanets form in protoplanetary accretion disks. This is important because the disk the birth environment sets the two most fundamental parameters of the planets, the mass and the distance from the star. So the mass determines whether or not the planet will be small and rocky, like Earth, or large and gaseous, like Jupiter. The distance from the star decides the surface temperature. So that decides in many ways the atmospheric evolution, for example, whether you have a runaway greenhouse or a runaway icehouse, like on Venus or like on Mars, for example. It's very important. So this image on the left-hand side that I'm showing you here is HL Tau. It's a very famous image. It was taken in 2015. And what you can see these dark gaps here. These are gaps that are being carved out by forming exoplanets. They're carving out all of this dust that you can see here. So if we want to understand the exoplanet architecture, we need to understand the conditions of formation in the protoplanetary accretion disk. Now, we have a timescale problem. Accretion disks, when we see them, are generally young, about 1 million years old, maybe even younger. In our kind of, classical planet formation paradigm, it takes many, many years, millions of years to form giant planets. We can't observe on these timescales, right? Something interesting happens here, about 10 to the 5 years, and then about 1 billion years later, you have a fully formed solar system like our own. What happens in the middle? So I have here a couple of simulations from some movies. On the left-hand side, the object is self-gravitating. On the right-hand side, it's also self-gravitating, but it's actually collapsed down to form some planetary mass objects, about 10 Jupiter mass or so. So these simulations are looped. They're about 3,000 years in Earth time. So we can't observe on evolutionary timescales over hundreds of thousands to millions of years, nor can we even really observe on dynamical timescales, thousands of years, right? We don't live that long. So we need models in order to interpret observations, because without models, we have all of this data with no understanding. So the most fundamental properties of exoplanets are set by their birth environment. So if we want to understand this exoplanet architecture, then we need to understand the early stages of planet formation and the early stages of the protoplanetary accretion disk, especially when it's massive enough to be self-gravitating and gravitationally unstable. Okay, so just to talk to you now a little bit more about what gravitational instability actually is. So accretion disks, as we know, are ubiquitous in astrophysics. They're found on every rung of the cosmic ladder, from active galactic nuclei all the way down to forming around exomoons. They exist because they form from a collapsing cloud that has even a small amount of velocity anisotropy. These collapsing clouds are huge. If one part of it is slightly nearer to some bright warm star than another, you're going to have an imbalance in the rotation, and it creates a huge amount of angular momentum. The only shape that can conserve the angular momentum is if it collapses down into a disk with the angular momentum vector pointing directly upwards. So what happens in an accretion disk is you have mass flow inward. That's kind of the purpose of them. Mass flow inwards in order to form a central protostar. But in order to conserve angular momentum has to be redistributed outwards. So if you had some mass element, some angular momentum, moving inwards, it's going to violate the conservation of angular momentum. So if you want your mass to move in, your angular momentum needs to move out.
Can I ask a question?
Yes?
Do you see a gap between the disk and the star, like in that graphic? Is there that big of a gap?
So this is somewhat schematic, but in general, you basically do have an inner edge that has been photoevaporatively cleared by the central star. So it's, this is exaggerated, but there is a bit of a gap there, yeah. Yeah. So the purpose of an accretion disk, if it can be so complex as to have a purpose, is for mass to move inwards, sentient all of a sudden, okay? It's for mass to move inwards so that the central protostar can grow. So these aren't static objects, they are dynamical objects that evolve over time. So we've built up a system of classification based on SEDs. This SEDs basically quantifies how much of the disk is left, because if there's a significant amount, an awful lot of the starlight will be reprocessed to longer wavelengths of the infrared. So the majority of the angular momentum is kind of carried away almost to infinite radius, while the majority of the mass ends up on the central protostar. So this equation is the evolution equation for disk surface density, basically changing over time under action of internal angular momentum transport. So what you can see here is this nu is some viscosity. So in order to redistribute angular momentum, you need a torque. In this scenario, this torque, this rate of change of angular momentum, comes from this viscosity. If you don't have this viscosity, there's no torque. This is a big open question in our field. What is the origin of this viscosity and therefore the torque? We need turbulence. The reason that we need turbulence is because an object that is in true Keplerian rotation is always in laminar flow. What happens is if you take a fluid element and you displace it out to large radii, there's always going to be a restoring force. Oh, hello.
I did manage to come to the talk. Can I ask a question?
Yeah, sure.
Well, can't we also distribute angular momentum with winds and get rid of you have a very low viscosity disk?
Yes, that is true.
Okay.
But I think that tends to happen later, when there is a significant amount of wind, coming from the star. It's not always clear to me that that happens very early on necessarily.
Interesting. Okay, thank you.
Where's... Okay. Okay, so the object in true Keplerian rotation, basically if you displace a fluid element, it's always going to have a restoring force acting on it, trying to push it back to where it originally was. So what this means is that there's no instability in this concentric laminar flow. You need some degree of turbulence to have it. So there are a few good candidates. For example, the vertical shear instability. It's a really promising candidate mechanism to produce turbulence in the outer part of the disk. Essentially, it has to exist in any disk for which there is a radial temperature or entropy gradient. The MRI is also likely to be very important, but I think this is not so likely to be important at early times. The reason for this is that it requires a significant amount of the disk to be ionized in order for it to be active. Very, very early times when the disk is very young, that's not clear to me that the temperatures are high enough for that to be the case. So the final option leaves us with gravitational instability. And the reason that this is intriguing is because it can happen when the disk is very massive, which happens when the disk is very, very young. So I just want to...
Just a question about
Sure.
That. So what about photonization? How is that normally not dominant?
So that tends to happen more in the upper layers of the disk rather than in the midplane. So you'd need, an awful lot of the disk to be, ionized right the way through to get turbulence at the midplane as well.
Normally too high of column density for it.
I think so, yeah.
Thanks.
Yeah. Okay. So I just want to introduce to you a parameter. It's called the Toomre Q parameter. And what it does is it essentially kind of demarcates when the disk can be gravitationally unstable. So it has to be less than about 2. So what we have here is we have our sound speed, we have our rotation, okay, all acting over the surface density of the disk. So what we have is the pressure component from the sound speed stabilizes shorter wavelength perturbations. The rotation stabilizes longer wavelength perturbations. Both of those are acting against gravity. Okay, if gravity wins, the Toomre Q parameter drops, and then basically you kind of get shock heating, and the pressure starts to increase and it goes back up again. It settles into a quasi-steady state. So for a Q of less than 1, you can have these ring-like disturbances, but they tend not to happen very often. And the reason for this is that for a Q of less than about 1.5 to about 1.7, you get these non-axisymmetric spiral modes that grow instead. Because these are easier to kind of get to, what happens is they start to kind of collisionally heat themselves up and push the tomb ray parameter back up again, so it never really kind of gets down to that Q of 1. It can in some circumstances, but generally speaking, when the disk is massive, it encounters this threshold first. So the disk over some time will kind of settle into a quasi-steady self-regulating state. So what does that mean? It basically means that heating and cooling are balanced. So you have this expression here for heating and this expression for cooling. And what we can do is we equate and we rearrange, and we get an expression that quantifies the efficiency of angular momentum transport due to the gravitational instability in the disk. It can also be thought of as an effective stress that is present in the disk, and there is a finite amount of stress that the disk can hold, a bit like a human, only so much you can hold on to, okay, until you lose it. So, okay, I've just thrown a bunch of equations at you, but what does that actually mean? So in the case that the disk is more massive, you'll get this stronger heating. If that's the case, stronger cooling is required to remain balanced. And you start to see these kind of really dramatic spirals, a big contrast between the spiral arm and the interarm region. On the other hand, if you have something that's less massive, you get weaker heating, and therefore weaker cooling is required in order for it to become balanced. Look, not very dramatic at all. These are quite weak spirals. Exactly the same. So for this situation where the disk is massive, we have a high alpha with an efficient angular momentum transport. In this situation, we have a low alpha, so we have less efficient angular momentum transport, and also therefore a lower accretion rate through the disk as well. So remember when I said there's only so much stress that someone can take? Okay, this is what happens if the stress is too high. You get something called fragmentation. So what happens with fragmentation is the disk cools faster than it can collisionally heat itself up again. If this is the case, it will collapse down to form gravitationally bound objects. So these here are two shearing sheet simulations. So in a shearing sheet simulation, you basically look at a small region of the disk. You pick a fiducial point that is co-rotating with the bulk of motion of the disk, and then you expand your equations of motion in first order, and you solve for those perturbations. So it really just allows you to look at a focus region of the disk. So here, we have fragmentation collapsing to form fragments because it was able to cool more rapidly than it was able to heat itself up, determined by this here. On the other hand, we have, oh no, my laser pen just died. I charged you yesterday, Judas. Okay. Is there another laser pen? No. Okay, I'll just gesture, that's fine.
There should be a pointer.
This thing?
Yeah.
Yeah, if you flip, you might need to flip this. Oh,
It's okay, I've got one. We're all good. Okay. So here we've got fragmentation, and here settling into a quasi-steady state. So in global simulations, you will have something that looks more like this. Okay, so in the global simulation, we haven't just expanded the equations of motion in first order anymore and just looking at this localized deviation. We're really looking at the disk as a whole. So if we go back one slide, back, there we go. Go back one slide, okay, fragmentation, quasi-steady. Okay, fragmentation, quasi-steady. So this is what it looks like in a global simulation. So a really interesting question is, when does fragmentation happen? So far, not a huge amount of data for objects undergoing fragmentation, but what's interesting is observations are showing that it's possible at all sorts of extremes. So for example, this 40 solar mass object here with a 0.6 solar mass fragment, fragmentation happens around here, but it can also happen on much smaller scales too. So this 1 solar mass binary with a 0.9 solar mass fragment as well. So in both kind of, really high mass star and a kind of a lower mass star, it's possible in both cases. What's interesting is that work led by PhD student James Cadman at the University of Edinburgh showed that fragmentation was actually favored around higher mass stars. So what he did was he ran a series of simulations, and I'm just drawing your attention here to the disk to star mass ratio. Look, it's the same in all cases, yeah? 0.5. So in all cases, the disk is 50% of the host star mass. But what we did was we increased the host star mass, okay? But the disk to star mass ratio remains the same. What we find Yes.
What's the spatial scale?
That would be helpful. About across here is about 300 AU, I think.
And is it the same on each
Yeah.
one, or does that scale also?
Same scale on all of them, about 300 AU.
No, but sorry, I guess I mean the disk itself. Or does the disk have constant surface mass density, or as you're going up the higher stellar mass is the characteristic?
Oh, I see what you mean. So the surface density profiles were always the same. They always had like a power law slope of r to the -1 for the surface density. I think the sound speed profile was always to the power of -0.25 or -0.5. I forget off the top of my head.
Right.
Yeah.
So then when the stellar mass went up, the disk scaled kind of like that.
Yes.
Right. So it's a more self-gravitating disk.
Yes, that's right.
So the same disk to star mass ratio, if you increase the stellar mass, the disk is more self-gravitating.
So well, the disk to star mass ratio is the thing that controls the dynamics in this case, right? So if you have, a lower disk to star mass ratio, say of about 0.1 or so, you're going to find that local angular momentum transport is true. You're going to have weak and flocculent spirals. It's really the disk to star mass ratio that kind of decides what the morphology of the system looks like. So I think that's kind of the important thing. We kept the profiles, the initial profiles and everything the same. So the disk to star mass ratio was always the same in all of the cases. So what James Cadman found was that as you increased the stellar mass, fragmentation was preferred around higher mass stars. And this is interesting because when we look at systems like HR 8799, it has a slightly more massive central star, 1.5 solar masses, and some of the other things that we're interested in with gravitational instability. This is a really neat system because in general, gravitational instability does not form planets. Okay, it's been proposed as forming terrestrial mass objects, but that doesn't really happen. What it does do is form higher mass objects further out. So this system, HR 8799, has got a few planets here of 5 to 7 Jupiter masses. And these things are on really, really wide orbits. And what's interesting is it's really hard to explain how we have a planet so massive, so far away from the host star. In our core accretion paradigm of planet formation, there's not enough stuff out there to form something so massive. But if it forms early on through direct gravitational collapse, then we shouldn't have a problem. So we find fragmentation produces predominantly massive objects very far away from their central star. And this is consistent with observations. So in 2017, Vagan et al. Took the VLT narco sample, combined it with a few other samples to get a total sample of 199 FGK stars. And what they found is that between 1 and 8.6% of systems had planets that were consistent with having formed through GI at a 95% confidence level. So what this tells us is that despite the GI planet pathway not being dominant, in fact, it's pretty rare, it's still the dominant pathway for systems that are themselves rare, like HR 8799. Okay, so I want to talk now a little bit about some observations. So just to introduce these images, so these top two images are taken in scattered light, 1.6 microns. Now with scattered light, you're typically probing material that is about 3 scale heights above the disk midplane. So really what you're seeing here are surface features. It doesn't necessarily mean that those surface features propagate down to the midplane. Indeed, for MWC 758, that's definitely the case, because we know it's a total mess if you look at it at other wavelengths. It's got all sorts of stuff going on. These two.
Sorry, what does that 3 scale height number come from? Is there an intuitive way to understand that? Like characteristic vertical profile or something? What
do you mean for the scattering? Or?
Yeah, you said for scattering your own.
Yeah, so that's basically the wavelength that you're going to see scattering from those photons. If you want to see stuff, further down, you're going to have to go through to longer wavelengths, basically, because it's just like optically thick. So you're just only going to be able to see stuff at the surface otherwise.
So it must be that there's some sort of roughly universal vertical density profile in order for that to be the tau equals
Oh, yes, I see what you mean. I don't know, actually, off the top of my head. Yeah.
Transfers that time.
Yeah. No, I don't know, but I'll find out for you and tell you if I find out. Okay. So these bottom images that you can see here, they're at the millimeter. So the millimeter, you're kind of probing down more to the midplane of the disk. So one of the problems that we've been faced with is the morphological similarity of spirals caused either by gravitational instability or by planets. Like if you look here, this is a real observation, the MWC 758 system. It looks very similar to both spirals caused by gravitational instability and also spirals caused by planets. So this is a bit of a nightmare. Morphologically, too similar to tell. The disk mass is often highly uncertain. Trying to look at these things, you're making an assumption about the dust to gas mass ratio, for example, that you just don't know what the dust to gas mass ratio is. So you could be off by a factor of 10. So this is really highly uncertain. We need another way. So the answer is to use kinematics and study the motion of these objects. So these are moving objects. They rotate. You can tell it's not perfectly uniform, right? So on the right, just to explain what you're looking at here, this is a continuum image of this disk from a radiative transfer calculation. So this is basically you just release a bunch of photon packets, let them propagate through the medium. Eventually, they scatter their way outwards and they're incident on some observational plane, and you're able to make your image here. So we can look not only at the continuum, but also at the gas. So this continuum background here, this is the dust. What we want to look at is we want to pin down what the velocity of these different parts of the gas are. So if we're looking at a particular line transition, like the 13CO J equals 2 to 1 transition, we know exactly what the frequency or the wavelength of that transition should be. So if it's anything other than that, it tells us that it's Doppler shifted. So either the gas that we're looking at is moving towards us or it's moving away from us. So here, looking at this particular channel, okay, channels have finite widths, right? You're going to be probing this region of the disk here. If we want to look at the stuff that basically has no radial motion along our line of sight, that's what we're going to be observing in this red triangle here. So remember, if it was infinitesimally thin, okay, we'd only be seeing, the gas in that straight line there as this thing was kind of rotating along our line of sight. So this is the V equals 0 kilometers a second channel. When we go round to the other side of the disk, okay, we'll see stuff that's kind of moving away from us, okay, and that's probing this part of the disk here. Just showing this because the first time I saw this as a student, it took me a second to get my head around, trying to make sure everyone understands what we're seeing. So one thing to note here is that there is no single point at which the velocity is perturbed in a self-gravitating simulation. The GI spirals are everywhere throughout the disk. It's pretty uniform and azimuth, and they're also present throughout the radius as well. And this is useful, and we can use this. So just to show you, in this scenario here, I've artificially set the gas velocity to be equal to exactly Keplerian, so p squared equals a cubed, and you get something called the Keplerian butterfly. So this is what you see when you look at an accretion disk, the Keplerian butterfly. So you can see here this distinctive perturbation. So the perturbations to the velocity distribution in the object caused by gravitational instability are very nicely analytically described by this work led by Longarini et al. In 2021. But you can see here this distinctive zigzag feature that is not present if the disk is exactly Keplerian. So this is kind of a smoking gun of gravitational instability. So I called it the GI wiggle. In hindsight, I probably should have called it the giggle for a good pun, and I was sorely disappointed in myself for missing it. But what's nice about this is it's present at all azimuths. It's independent of viewing angle. So kind of no matter what you do to the system, apart from putting it exactly edge on, you can pretty much always see it. So it's a really robust and strong signal of gravitational instability. So just to explain what's happening to cause this wiggle, on the left-hand side, I've got a moment one map, and I've traced out the line of that delta V equals 0. You can see you get this kind of interlocking finger structure. Then taken that and traced it out just so that you can see here. So basically we have sub and super Keplerian inside and outside of the spiral arms. And what that does is it steals emission into neighboring channels, okay? So this has had some emission stolen from this channel, but it's also had some pushed in from the neighboring channel as well. So rather than getting these straight Keplerian cones or Keplerian butterfly, you get this distinctive zigzag feature instead. The key question is, have we detected the GI wiggle? And the answer is yes. You know, when I first started talking about this, I was like, oh, it's tentative. But now I'm a little bit more convinced, I think. I don't know if it's just because my faith in myself is growing, unsure. But this tentative evidence was found by Teresa Panat-Carreño, who's now a PhD student at ISO. So what she did was she took this data of the Elias 227 system, and you can just see this faint wiggle shape. So what she did here was just trace out the maximum of the intensity. You can see this kind of distinctive wiggle-like shape. So what I would say is that we need follow-up observations to be sure, you know, we always want higher resolution and higher sensitivity, right? But a key question is, how do we disentangle this kinematic signature from other kinematic signatures that may not be gravitational instability? So just to walk you through a couple of other options. The first is a planet. So planets also cause a kinematic signature. This basically is called a velocity kink. It looks a bit like an elbow shape to me here. So planets have this localized kink because what they're doing is they're perturbing the gas most strongly at their location. And then because the disk is viscous, this difference in velocity is kind of smoothed out a little bit as you go around the disk, so you don't see it so dramatically. So for planets, that perturbation is kind of localized, so that's probably easy enough to distinguish, maybe. The vertical shear instability could certainly be confused with gravitational instability, especially if it's a low mass system, because then it will have a higher number of spiral arms. So definitely that could be the case there, but maybe not so much if the disk is a very high mass, because it will have a lower number of spiral arms. So GI does also produce this, you know, quite dramatic, distinctive interlocking finger structure, which is not really the same as in the VSI. But one of the key points is GI is very non-Keplerian everywhere. So a GI disk is basically super Keplerian because it has this significant contribution to the gravitational potential from the disk's self-gravity. So we can take advantage of this by looking at rotation curves, which we'll do in a second. So the GI wiggle can be used to constrain the disk mass. This was work led by Jason Terry, who's a graduate student at UGA. And what he realized very cleverly was that basically the wiggle has a wavelength and an amplitude, so it's just a wave-like feature. So he ran 7 simulations of different disk masses. And basically what he found that a larger disk mass has higher amplitude spirals and a larger separation. This isn't new, we already knew this. But what that translated to was a much larger amplitude wiggle. So plotting the amplitude of the wiggle, plotting the amplitude of the wiggle and the wavelength of the wiggle, you can see that it kind of has this roughly kind of linear relationship. It's a little bit messy, the error bars are large. So there is certainly a positive relationship there between the disk to star mass ratio and the wiggle wavelength. The problem is that disks are only truly quasi-steady when they have a very low mass. So when you start to go up to higher masses, you basically get kind of periods where they, you know, the spirals are very dramatic and they calm down, they're dramatic and they calm down. So it's hard to say, okay, I have to take a time average of this, which is kind of where a good chunk of the noise comes from. So we can also describe this analytically by perturbed surface density and perturbed potential equations. So this work was led by Cristiano Longarini, who's a PhD student at the University of Milan. So I want to say, with a lot of algebra, substitution, and wizardry, he sent me the draft of this and said, can you please check my working? And it took me 3 weeks of only working on that. But you can basically get an expression for radial velocity perturbation and also the azimuthal velocity perturbation as well. So it's really nice that we also have a nice analytical description of the GI wiggle as well, not just the simulations too. But the problem, bit of a spanner in the works, was that this work realized that the amplitude of the wiggle is not only proportional to the disk to star mass ratio, but it's also a function of how quickly the disk is cooling. So what this means is that the amplitude of the wiggle is degenerate with both the disk mass and how fast the disk is cooling. So in order to break this degeneracy, we have to use a rotation curve. So for a cool, slowly accreting disk, you're required for centrifugal balance that equation 1 be true. So you basically have, kind of your normal Keplerian expression, your radial gravitational field of the disk, which in a massive disk is important, okay? And then also the radial pressure gradient as well. This is difficult to solve, but it can be solved analytically. In fact, it was solved back in 1999 by Burton and Lodato. So what Benedetta Veronesi did in 2021, she took this and she fit to observational data. So using this, she went after the Elias 227 system using data from Teresa Panak et al. 2021. So I realized that this very messy plot doesn't necessarily look super convincing, but actually what we have in the analysis is that the Keplerian fit is rejected at a 97% confidence level. So we're pretty sure actually that this disk is non-Keplerian. So using the expression that I just showed you, Benedetta recovered that the disk to star mass ratio for the Elias 227 system is 0.4. The threshold for GI to set in is usually about 0.1. So we're able to kind of demonstrate that this spirals that we see in this system are probably due to gravitational instability. So if we combine the GI wiggle with this self-gravitating rotation curve, combine the two together, I think it's fairly compelling evidence that what we're looking at here is the GI wiggle and not some other effects such as the vertical shear instability or some planets that we can't see. Okay, so I want to talk to you a little bit about some works in progress. So this may be significantly less polished, but I'm excited by it, so I wanted to share it with you. So searching through velocity channels by eye to look for features in kinematic data is not really ideal. It's kind of fine when we have 10 systems or so, as was the case a few years ago. But now it's growing and it's growing, and ALMA's kind of moving into survey mode, and we're just seeing more and more and more of these systems. It gets very difficult to do by eye. Data is noisy. Humans also make mistakes and miss objects. That maybe not so much when you've got hundreds of people looking at the same data, but it can and does happen. So really what we would like to do would be able to automate the search for planets or gravitational instability. So we can do this using machine learning, in particular using convolutional neural networks. So just to explain, a convolutional neural network, what happens is you have some inputs, which are usually some pixel values. You give some weights to these inputs. You basically take a sum, you apply some nonlinear function, and you get an output. In a deep neural network, all of these things are connected together. So you have more and more of these neurons connected, doing the same thing over and over together, connecting these perceptrons. But what happens here in a deep neural network is you lose spatial information. You want to keep hold of spatial information when you're looking at images. That's what a convolutional neural network does. It basically has a filter that slides over a series of pixels. In doing so, it keeps that spatial information, and it can tell you what's important spatially in that image. So just to give you an example, a CNN will activate on regions that it thinks are important in classifying this animal, whether it be a cat, a dog, a fish, a goat, whatever it is. It's decided that in classifying this animal correctly as a cat, the features that are important are the eyes, the nose, and the tabby stripes here, and a little bit the whiskers too, okay? But the brighter parts are the parts that it thinks are important. So we can take this exact same idea, and we can apply it on simulation data and also real observational data as well. So Jason led this work by training on simulation data, testing on simulated unseen data. So this is hidden from the user, from the neural network, sorry, it doesn't see it, and then applying on real data as well. So the good thing about applying to unseen data is, of course, we know what the answer should be. So Jason here has been measuring disk mass by using this. So basically training on thousands of simulations that we've done, passing it to neural network, and it tells us, okay, these are the regions that are important in correctly regressing to some mass here. So I think it's improved significantly now. I think actually it's doing much better, and its accuracy is, you know, like the 2%, 3% level, something like that. So it's doing pretty well. But this architecture is really powerful because not only is it able to measure disk mass, but we're also able to do things like apply it on real data and confirm that we're right in that these planets are there. So we've trained this only on synthetic data. So training on synthetic data and then applying to real data actually has a pretty you know, powerful pedigree in other fields like medicine, for example, or autonomous cars. Hasn't happened so much in astronomy, or certainly not in protoplanetary accretion disks yet. But this is really nice because it's a proof of concept that shows that if you take synthetic data from simulations, you train your machine learning tools, you can apply it to real data and it works. So that's what we found here. So we're applying this architecture to find planets in real data. So this is really nice. At the moment, this is our working title. It stands for Deep Computer Vision in the Astrophysics of Planet Formation, also known as the world's most tenuous backronym. I don't know if the name will change or not, but that's the name we're giving it at the moment. So we find planets as well that humans miss, that we know for sure humans have missed. So in simulation data, we know a priori that there is a planet there. So it will find planets that humans miss. So it's faster and more accurate than a human searching for forming exoplanets in this synthetic data. So what's interesting is that, you know, I looked at this, you know, it was double blind, whatever. I was just given a load of data. Look at this. Is there a planet there or not? I said there wasn't, and I was wrong. And our machine learning architecture was right. So we're ultimately going to release this as a package to be able to search through kinematic data for detection of exoplanets and analysis of disk mass. It is not user-friendly right now, so that's going to take us a little while, I think, to get to that stage, but watch this space. Okay, so I want to talk about another work in progress. So we have to know a definition first before I can talk about this. So I'm introducing to you the Stokes number. So this A here is grain size. This rho S is the intrinsic density of the grain, usually about 3 grams a centimeter cubed or so. Okay, and this sigma G is the surface density of the gas. So we have a couple of scenarios that I'm showing you here. For a Stokes number that's very, very low, solid particles are coupled perfectly to the gas. They just follow the gas flow lines, no problem. At the other end of the scale, these flow lines here, these particles just don't care. When it's really, really massive, they're just completely unperturbed. The gas just flows around it. A little bit like boulders in a river. They just don't care. They just don't move. So that's what's happening in this scenario. Here in the middle is a really interesting case where the Stokes number equals 1, because you start to get all of these really interesting effects, like particle trapping and buildup, a little bit like a traffic jam when you get to a traffic light. So you start to get these particles building up and concentrating in certain areas. Okay, so what does that look like in global simulations? Well, it looks a little bit like this. So these are some simulations. This is, in fact, it's all one simulation. They all just have different grain size of dust. So here is a micron size dust, perfectly coupled to the gas. It just traces the gas exactly. Here at centimeter sizes, okay, it's starting to get a little bit more interesting as it's approaching the Stokes number of 1. And you can see that the spirals are really increased quite a lot in the center because the dust is concentrated there. So I was curious about how dust impacts the growth of gravitational instability. So I started on this project looking at different dust to gas ratios. So I started with a dust to gas ratio of 10 to the minus 3, so depleted relative to the interstellar medium, then also increased relative to the interstellar medium. So here 10 to the minus 3, 10 to the minus 1, interstellar medium is 10 to the minus 2. And in fact, when I started this work, in my notebook, it was called dust back reaction suppressing GI, which is the exact opposite of what happens, it turns out. So here, what I have is this tomb ray parameter. Remember that says how stable this disk is. And then basically what you have is that when you have this, large amount of dust to gas, yeah, okay, it's true that from, the tomb ray parameter, it seems to be more stable. But look, the gravitational instability is clearly stronger in this bottom situation where we've increased the amount of dust. So what's interesting is it seems to be the case that disk is more unstable for the higher tomb ray parameters. The disk mode spectrum changes basically because you have more power in this kind of 2-arm mode. It looks, more like a 6 or 8-arm mode here. I'm unsure about this, so if people want to chat to me afterwards, I've been chatting to people about this today. If you have any ideas to share, please throw them my way because I've been a bit stumped by the whole thing. Okay, so another work in progress. I'd like to take a sharp turn on the exit ramp. So over the last year or so, my interest in astrobiology has really been piqued, I think especially with the launch of the JWST. Truthfully, this is probably a more honest slide, but I do try to keep my chronic inability to take anything seriously in check. I failed, obviously. Okay, so my question is, where is life possible? I originally started thinking about this, like I mentioned, because of the launch of JWST, and people were floating out ideas that maybe it would be possible to detect, signatures like oxygen. But the issue is that you would need about 700 transits to be able to detect something like oxygen. So I was like, okay, even at the TRAPPIST system, that's going to be longer than the planned lifetime of JWST, so it's just not going to happen. But there are lots of other things that basically act as like secondary markers of oxygen. It can be things like chemical disequilibrium that happens because there's a lot of oxygen in the atmosphere. So then I felt hopeful again that there are biomarkers out there that we could search for even in our lifetime. So we're probably all familiar in some way with the habitable zone. The habitable zone says, I can find liquid water here. So here you have your host star mass going this way, planet semi-major axis going this way. And this strip in the middle here is where you can find liquid water on the surface of the planet. So it's called the equilibrium temperature of the planet, where the radiation coming in from the star matches the radiation going out. What temperature would you expect this to be? Doesn't include anything like atmospheric greenhouse. So you calculate this from stellar fluxes, then you get some distance here. So almost all life on Earth in some way depends on oxygenic photosynthesis. You can have anaxygenic photosynthesis, that doesn't change the atmosphere. You can have chemosynthesis, doesn't change the atmosphere. If we're going to detect biosignatures or potential markers of life, you need something that changes your atmosphere. Oxygenic photosynthesis is rate limited by 4 things. 1, water abundance. 2, carbon dioxide intensity or concentration. 3, light intensity. And 4, temperature. So really, this idea of this biosignature zone is going to tell us where photosynthesis is possible. So the habitable zone tells us where we can get liquid water, and the biosignature zone tells us where we're going to get photosynthesis. So I trawled the literature and became a biologist for 6 weeks. Okay, and I found one thing in common, well, several things in common. I was looking particularly at any kind of photosynthesizing bacteria. And what I found was that they were all described by rate curves. So a rate curve is basically an optimization function. So your rate of photosynthesis measured in micromoles of oxygen per milligram of biomass per hour. Okay, so that's how much oxygen is being produced as a rate. Okay, it's basically a function. If you say, okay, I've got unlimited water, I've got unlimited carbon dioxide, which is not unreasonable if you're in the ocean and you have a secondary atmosphere. Okay, then you're only limited by your intensity and your temperature. All of these things for all of these species could be described by curves functionally like this one. So of course, the peaks would change, the slopes would change ever so slightly. Qualitatively, they are the same. You have some sharp peak for light intensity, a max, and a slow drop off. For temperature, you have a slow buildup, a peak, and a sharp drop off. You can combine these two, which is what I did here. So a key point that I want to highlight is it includes your rate of respiration. Your rate of respiration stays about the same. It's what you need to keep you alive and to do all the things like move, reproduce, grow. You're only going to get a net positive photosynthetic output in terms of amount of oxygen produced if your photosynthesis rate exceeds your rate of respiration. If it doesn't, if the conditions are not ideal for photosynthesis, your respiration rate is going to eat up all of that oxygen and you're going to get vegetative die-off or biomass die-off, and life is not going to be able to thrive. So the key here is we would be able to find examples of photosynthetic life wherever this p-value is positive, okay? So the pink region here, that is where photosynthesis is possible, considering only light intensity from the star at photosynthetically active wavelengths and also the temperature, okay? So if I say, okay, let's say this planet has got no atmospheric effects, so no greenhouse, no photon attenuation, great. Where we could expect to have biosignatures is pretty much throughout the habitable zone. Bad news for things around lower mass planets. Around here, it's a bit less likely. Moderate atmosphere, maybe a bit more like leaning towards something like Mars, for example, although its greenhouse is a much higher greenhouse than on Mars. And say, okay, maybe not so much attenuation, significantly more attenuation. What do you have? Well, your habitable zone starts to become much more narrow. Okay, becomes much more like a sliver. For an Earth-like atmosphere, where you have a greenhouse effect of 30 Kelvin, and actually only 20% of the photons that are incident at the surface of our atmosphere make it down to the Earth, to the surface of the Earth. Okay, so you've got a greenhouse, you've got this attenuation. What happens here? So say Earth-like, okay, only in photon attenuation and greenhouse effect, disclaimer, okay. You have this really narrow sliver here where you could expect to find photosynthesis. So, conclusion, most of the habitable zone might not be habitable. This biosignature zone is where we should concentrate our transit spectroscopy searches if that's what we want to do. Some limitations, I didn't consider planet mass or detailed atmospheres. That's to do next. Rate curves are species specific, but they all follow the same sort of shape. The big one is it assumes life is Earth-like. There's a common hypothesis that if there's life in the universe elsewhere, it would be wildly unrecognizable to anything that we have on Earth. But is this true? I say maybe it's not so true, because there's a good chance that life is probably similar at the subatomic level. You know, life has to be out of equilibrium with its environment. In order to do so, it has to take in some energy from its environment and use it to do all of the things that life needs to do. Life is also probably similar at the atomic and molecular level. For example, carbon, it's ubiquitous. You know, the 5 carbon sugars are basically the smallest things that can form ring-like structures and give structures to other things, like biochemically. Water is very abundant for a solvent. Why choose ammonia when water is so abundant in the universe? People always say, oh, what about silicon-based life? Well, my dude, we have billions of years of examples of silicon forming rocks on Earth, not life. So I don't think that's super likely. Maybe there is some biochemical variety. You know, we use 20 amino acids on Earth. We know that we've observed more than 60 elsewhere. So, okay, yeah, maybe that's true. We could use those, but we'd still have to be constrained by function. You know, you can change the body, the chassis of a car, but it still has to have some sort of engine, you know, driving it at its core. So the function still has to be the same. Yeah. Oh, thanks. It's okay. So just to summarize, GI may provide the turbulence needed for accretion to happen. Spiral morphology can be GI. We really need kinematics in order to kind of pin it down, such as the GI wiggle or rotation curves. some early results using machine learning to measure disk mass from the wiggle and planet mass from the velocity perturbations. Also finding that dust increases spiral strength. I'd really like to chat to people about this, so if anyone's interested, please come and give me your ideas, because I've been a little stumped by it. And also, most of the habitable zone might not actually be habitable. Okay, thank you.
Right. So we've already had rather a lot of questions. Are there any more? Yeah.
Hey.
I'm really fascinated by this idea of the having overlap in the photosynthesis zone and the thing. One thing that I'm curious about your thoughts on is that when you look at different stellar host types, you're not just changing the total influx, you're also looking at a very different peak of your spectrum of what wavelengths you're looking at. And so how does that kind of affect things? If we're looking at photosynthesis, there's multiple photosynthetic pigments even here on Earth. And if we're thinking light might be optimizing for a much broader spectrum, we're looking at a different, a different pigment might have different chemistry. So what are your thoughts on that?
Sure. So I spoke, so actually on the paper that I've just submitted, one of my colleagues is a biologist, precisely to stop me from saying anything stupid about this. So while that's true, I was only looking at, what we consider, so the 450 kind of to 700 nanometers that's used for photosynthesis. So it uses this particular molecule called chlorophyll A. So all of the rate curves and everything that I showed you were all for chlorophyll A. Because the infrared, the exotic photosynthesis at longer wavelengths is really poorly studied. I couldn't find any examples for rate curves for these things because they're really, really difficult to grow in a lab because the cyanobacteria has a doubling time of like a month. So that could definitely be true. In my models, I was careful to, bin the wavelengths correctly and all that sort of stuff. But I don't know what the rate curves would look like if we were going to, look at longer wavelengths. But it's definitely possible, because in some exotic photosynthesis on Earth, for example, that uses infrared radiation, it's also anoxygenic, so you wouldn't see it in the atmosphere anyway. It uses something else as the electron donor, I think hydrogen sulfide. So that's kind of complicated too. And the examples that we have on Earth that use longer wavelengths, they tend to be either anoxygenic or use something else as the electron donor. But happy to chat more afterwards. Okay.
Any other, John?
Really amazing stuff. I was curious if you could say a few more words about the technical details of the simulation. Like, for example, does the viscosity arise naturally, or you put some in? Like, what's the cooling?
Yeah, okay. So I use smooth particle hydrodynamics. The reason I use that is because it kind of naturally takes care of the resolution. It puts it where you want it. So for most of my simulations, I use a million particles. You don't have to put in extra viscosity because that's kind of provided by the gravitational instability. So it's not like when you just have a planet, for example, and you'd have to change whatever your physical alpha parameter is in that way. What else? Yeah, I use a one fluid prescription as well, rather than a two fluid. So a one fluid prescription, basically every SPH particle will have a dust fraction associated with it. And that's smooth like all the other quantities. And then you basically solve it as an advection on the mixture.
Any other questions? I have a question because you mentioned at some point like you'd like higher angular resolution from ALMA. Is that top of the wish list? Is it more ALMA bands? Is it more systems? Like, what's the limitation in terms of getting the observations to constrain the models?
So we've got like higher angular resolution for some of the planet forming systems. So it's certainly, the planet containing systems with the velocity perturbations that I showed you. So it's certainly possible. I think for me, I think it would be a higher angular resolution to really pin down if that is the GI wiggle or not. I would really like to see that, but obviously you're fighting with people with different opinions.
How long would you be proposing for just for one system?
I don't know, probably like 10 or 12 hours maybe.
Not bad.
Yeah.
Sorry. Any other questions? Oh, yeah. Sorry.
Also about the biosignature zone, I think you said that you would need all the carbon and water, or all carbon and oxygen in order to produce this, which you can get if you're assuming you're underwater. So then I was curious if your model assumes that like all the intensity of the star gets through the water, and if there's any like assumption about whether the water's dirty or something like blocks that intensity.
Yeah, so that's a great question. So basically, okay, we don't know what the first species were, right? But one of the things that we do have, you know, the earliest example of like fossilized life is basically benthic mats, right, that are fossilized that we see in the Western Chert. And you can see these in stromatolites, you know, on the coast in Western Australia now. And it's really kind of only the very top layer that kind of does the photosynthesizing. So I haven't taken into account any of the Z effects. My next step is to do that by using, basically there's a series of like differential equations that balances oxygen transfer, hydrogen sulfide transfer, carbon dioxide abundance and water abundance through a benthic mat using differential equations. Rather than just using the parameterized rate curves that I showed you. That is my next step. I'm about 30% of the way there. And I haven't figured out how to get temperature into that yet, because ultimately what I want to do is explore the habitability possibility of super Earths and how that changes. So that's going to be my next step there.